Okay, well, have a test coming up. Now we need to get in and start talking about momentum a little bit. But right now, let's just take a few minutes and see what you need. No, because I don't give formula sheets. I think that's my way of thinking. It's a terrible thing to do. But a lot of good universities do it, colleges and so forth. That just started back when I think people gave up having people actually learn physics. I'm not sure what the thinking behind that is, but let me explain here. What do you need to know? Acceleration is constant, you get the equations of motion. You should know that. You should be able to derive the equations of motion from that, although I won't be asking you to do that in the test. If you know what we did in the first week, then you know how to get the equations of motion in case you forget them. Otherwise, you're just better known, right? That's the equation of uniformly accelerated motion. You got to know that velocity is a derivative of position, acceleration is a derivative of velocity, right? Okay, so that's good. And I'm not sure you're going to need the derivative and integral relationships on this test, but you are going to need them in the course. You should know them. I mean, again, all this we did like almost from the first day. And we did the same thing with omegas and alphas and thetas or rotation. And you need to understand rotational motion, at least to the extent that it's done in chapter 3. Okay. So all this is just general knowledge. Then that force is mass times acceleration. And I could say up here, because these are all vector relations. And that really does kind of come into projectiles, even though you're not going to integrate them or anything. Okay. Anyhow, your net force is mass times acceleration. Yeah, that's the sum of forces. Now, I'm not even going to mention trigonometry, free body diagrams, except to put it down here. You got to know your trig. Right now, all you need is right angle trig. Okay. Trig vectors, free body diagrams. We can take this and say that I don't really have room to write it. net X force times I plus net Y force times J equals mass times acceleration times I plus acceleration times J. The X acceleration times the X component of acceleration and so forth. The projectile might be hard to read. X and Y motions are independent except for shared time. No, there's a time between two events. The same time runs the same for your X motion as it does for your Y motion. So you're solving the equations for T for your X motion, then you know what T is for your Y motion, okay? And vice versa. I don't think you're gonna need the general equation for circular motion. But what you do need to know is the triple acceleration is V squared over R. The centripetal force is mass times V squared over R. That is toward the center. Net work is a dot product of net force and displacement. Which is equal to change in kinetic energy. Kinetic energy is 1/2 mv squared. This is a frictional force, which will be less than or equal to the, this is static friction, which is less than or equal to the coefficient of friction times the normal force in its opposite. It's opposite when you add up all the other forces other than the friction. Kinetic friction equals coefficient of kinetic friction times the normal force. And let me just demonstrate something related to that. Let me just grab a call this a beam is the way we use it, this rotation. Okay. And we've seen it before, but watch again. Okay, what's your coefficient of static friction? Higher than I would have thought. There's a piece of sticky stuff on this, and I just happened to put this on there. That was ridiculous. Okay, I don't know how sticky stuff got on there, so can't be eaten during lab. Don't slobber on the. Okay, here we go. Well, okay, there was a slope, right? What's the coefficient of friction? How do you get the coefficient of friction from that slope? It's the tangent of the angle. And the tangent of this angle, which looks like it's somewhere between 30 and 37 degrees, okay? Tangent would be around the 0.4, 0.5 range, okay? Now you notice that when static friction ended, all of a sudden you were in kinetic friction, right? If you want kinetic friction, you just keep tapping this thing until the thing slides. And be prepared that time so you can catch it. Okay, now that's a lesser slope. Now I'd explain static and kinetic friction. And if you break static friction and the force is still there because what force was acting on the net force on the thing, course, when it was static, it was zero, but you add up all the other forces and you end up with the component of gravity down the incline. The normal force is equal and opposite to the component of gravity perpendicular to the incline. Okay. And the component of gravity parallel to the incline is what's essentially pushing the thing down the incline. It's actually the sum of all the forces, but that's what it comes down to. Everything else kind of cancels out. As soon as we break the static friction, we're into kinetic friction, and the thing accelerates pretty rapidly. Make sense?
Yep.
Well, you need to understand that. And that does appear in the test in one form or another, at least once, maybe more. Okay. And this is a work energy theorem. You got to know how to use it. You don't need a formula sheet. If you do need a formula sheet, it's because you're not well prepared. Okay. So make sure you're prepared. You know, that is a formula you can use. That's a formula, but it's also something that ought to be deeply ingrained in your brain. Okay. Hopefully in your gut and your brain, because they're connected. And if you connect everything, you have a better understanding. Okay. You got the equations of uniformly accelerated motion. I sure as heck wouldn't give you on a formula sheet, even if I used a formula sheet. Now, there are exceptions to that. There are a couple of places in second semester. I don't give you a formula sheet, I give you an expression sheet. Like I give you the expression v squared over r, just to remind you that v is squared. Okay. And of course, if v isn't squared, you don't get the units of acceleration. Now, y'all been following engineering habits and not writing units on a lot of your calculations and your work. And I've been nagging you to do that, and you're gonna wish you had, because I really have to see them on the test. Okay. Do the dimensional analysis. Either embed the units in your calculations or do the dimensional analysis out. Don't just say, well, that's a force and that's a mass, I multiply them, it must be newtons. Put the forces in dynes. Put your masses in grams. Put your accelerations in centimeters per second squared. It's not 9.8 anymore, is it? Okay. So I'm still seeing some of those mistakes. Also on your homework, I'll just mention that I'm not seeing a lot of detail in your reasoning. If you give me a really well-constructed solution that shows me the steps in your reasoning, that's fine. You don't need to put a lot of words around it, but you should put some words in it. You should get used to putting words into to show me your reasoning, because it's not so much that I need to see it, although you might come up with something unique and I might learn something. But because you need to be able to do that because you understand it much better. Okay. Okay. If you don't know that the net work by the net force is a dot product of net force and displacement and know what that means, well, hopefully you've done the problems and know what that means. Okay. Because the way you prepare this is to solve the problems. That's the test. And understand what's going on in lab and analyze what goes on in lab. Because you have really hands-on experience with that. It's your main connection. Now, as I said, everything is associated with lab situations. Okay. And things that we've talked about. So I'm not pulling cosmology out of the hat and asking you questions about cosmology, although you can kind of expect some of that on the exam. I mean, just, just as it comes out of the basic physics. Okay. So this stuff tells you everything you need to know, if you know it. Okay, that makes sense. Okay, I can't think of anything I'd want to add to that right now. There's probably something I should, but question came up. Okay. Now, you've got this time I think to do today, and I checked the email early this morning, but it's a test coming up. I understand you might be a little bit late with some of your homework, but assignment's going to keep coming. Unfortunately, between hurricanes and other technical issues and so forth, it's put us a good week behind where we need to be. Maybe a week and a half. Figure out how to maybe omit a couple of things. All right, I want to talk about momentum. So here's an example of momentum. I'm not sure I can do this. I think I can. Yeah, I got a trigger finger. So, okay, got my hand nice and relaxed, and I'm going to hit it with this hand. Okay. Now there's momentum. This fist had momentum, just a little tiny bit of momentum in my case, but it had some momentum. Okay. And when it hit this hand, this fist kept going a little bit. Okay. But a lot of the momentum transferred to this hand, which has pretty much the same mass as this fist. Now, this fist had the mass of my forearm and part of the mass or around my shoulder and stuff like that. We don't want to talk too much about the angular momentum, but so while this fist had no more mass than this hand, all the mass of my forearm was behind it. Now, the mass of this forearm is involved too, but most of it's down here, and there's a lot of leverage on this mass because it's being moved by force up here. So there we have it again. You can try to analyze energy, but the kinetic energy, when it hits, you know, I'm gonna have to stop doing this because you see some of the kinetic energy goes into pain. Well, not really. It goes into heat, basically. So my left arm's getting kind of hot. Of course, I've got blood circulation that prevents it from getting too warm. And also, talk about energy conservation. Where does the energy to accelerate this come from? Well, like any good American boy, I had Cheerios for breakfast this morning. And the unit of energy in a human body is the Cheerio unit. So when I started accelerating my fist, my nerves sent this message to my Cheerio repository to burn some Cheerios, which created the energy to contract my muscles and make that happen. Okay, see, I know a lot about physiology. Well, seriously, there's energy conservation, there's glycogen and all that stuff. You know, I haven't really looked at a complete explanation of that and all chemical pathways. Someday I need to do that, so I understand it better. Energy is not conserved. The kinetic energy before collision, the kinetic energy after collision are different. Okay, so you can't analyze this collision using energy. There are elastic collisions. Like if a pool ball hits another pool ball, well, there's rotation involved and that complicates things. But basically, you've got a pretty close to perfectly elastic collision, where if neither ball was spinning, the kinetic energy would be pretty close to being conserved. In most other collisions, it doesn't happen. Like if I clap my hands and have them relaxed when they hit, they'll tend to stick together because of the squishiness of my hands and stuff like that. Okay? All the kinetic energy gets lost. It goes into heat. If you clap your hands hard enough, fast enough, you'll feel them warm up a little bit. Although your blood circulation takes that heat away pretty quickly. Okay. The thing that is conserved in an isolated system is momentum. When two things interact in an isolated system, total momentum stays constant. Okay, so I'm going to give you the background on where momentum comes from. Remember that kinetic energy comes from you should never be without this connection because you know that formula just fine. It's the one you've probably used more than any other. And we derive this. You can't read it, just rederive it yourself. You just replace A by F net over M, which is Newton's second law, right? And rearrange it, then get this. So you got the change in kinetic energy equals the weight by the net force. Okay, well. To the right. Another equation of motion, really straightforward one with obvious interpretation because A delta T is how much the velocity changes because of what acceleration is. Very simple step, multiply both sides by M and subtract off your MV naught. And you got this. Very simple derivation. And well, this F net delta T is impulse. MV is momentum. Here, let me write it with MV. Now I'll write the traditional symbol. So this equation here's impulse, here's change in momentum. Now I'll try to write a little neater because this stuff is very straightforward and easy to understand. The conceptual part is just modestly challenging. It's not too bad. You got two masses in a closed system. And what's a closed system? A closed system is one in which the only forces are between the forces between the two masses. It's nothing outside. Okay. Now, when I did this, and then we're really not talking about a closed system between, let's say, this form, this, and this form and this, because everything's attached, attached up here, and more or less attached at this elbow. Okay. So there are forces being exerted on this forearm and this forearm by other things like the rest of my arm here. Okay. Makes sense. And if I really want to hit it, I get the rest of my body into it. Okay, the old Mike Tyson uppercut. He's better at it than I am. If I throw a good uppercut, I just break my hand if I hit anything. Not that I could throw a good uppercut. Two masses in a closed system. Okay, meaning again, no external forces. Okay, so I'm just going to write that, and you can read and work that out. let's say we got M1 and M2 and they're on a collision course. When they hit, they exert equal and opposite forces. Okay. If you isolate M1, make a free body diagram, M1 is represented as a dot and it experiences a force from M2, right? And M2, it experiences a force F1, 2, the force one exerts on 2. And I'm not sure I've got those subscripts right. This might be 1, 2, and that might be 2, 1. I didn't get a good explanation of that when I first encountered it in physics. And I've always been confused about it. I've always got to look and see what the convention is, and I didn't bother to do that. I scanned all the remaining chapters this semester last night. Okay, see how everything's approached, and I forgot to look at that. So this might actually be F1, 2, this might be F2, 1. You can check your book. Okay. But the point is, however they're indicated, what can I say about these forces? The forces are equal and opposite. So write down for me the expression for the acceleration. Uh-oh, we're out of focus again. Where's my picture? Oh. Sometimes it likes the lighthouse. I can't tell from here whether it's focused, but it's not. There it goes. Okay. No, am I recording? Yeah, okay. A1 is acceleration of mass 1. So what do? You look at the free body diagram, see what the net force is, right? This is the only force because there are no external forces. The only forces are the forces that these two things exert on each other. So A1 is F1 over M1 and A2 is F2 over M2. Okay, now which acceleration is going to be greater? Okay, so I think I said which force is greater. People looked at me confused because their forces are obviously equal in magnitude. Somebody finally said that. And then we got there, I'd said forces, not accelerations. So if I asked which acceleration is greater, well, I quickly got a good answer, the one with the lesser mass, right? You divide by lesser mass, you get a bigger result. The forces have the same magnitude. The one with the lesser mass is going to have the greater acceleration. Okay. Now there's a little more. What's the change in velocity? The change in velocity is the average force times the time interval. Okay. Now what I mean, why do I say average force? Well, two balls come together. Just imagine my fingers grasping the two balls. They come together, they squish together. and then they push apart. Right? Now you don't think of that with pool balls or steel balls, but they do. They compress a little bit. And they're very elastic. You don't think of steel as being all that elastic, but it is. And you get most of the energy coming back to it. That's what elastic means. Elasticity is a little different than just the property of being elastic. There's more to elasticity in a sense, so we don't worry too much about that right now. The point though is that if the objects are very elastic, then they're actually going to maintain most of the kinetic energy. All right. Well, back to what's the change in velocity? What's delta V1? I'll say A1 bar delta T, which is F21 bar over M1 delta T. What's delta T? It's the time the two things are in contact because they don't exert forces on one another when they break contact. Now, if they're magnets, that's a little different because they do exert forces at a distance. And if they're gravitational masses, they exert forces at a distance. So F21 delta T equals M1 times delta V1. Just multiply both sides by M1. Make sense? I want you to understand this, because what happens is you don't completely understand what I tell you or what you read in the book, and then you go try to solve the problems and you start pulling out equations and you don't know what equation to use. You don't go back to the concept, okay? And that's a strong tendency. I mean, I'm rereading Susskind's book on universal gravity, on Einstein's theory of gravitation for about the fourth time. And I keep seeing things that are obvious that I missed when I read it the third time. Okay. And I'm doing it without writing it out. If I was writing it out, I probably wouldn't need 4 readings. Okay. It's very challenging stuff at my age. And something I never had a chance to learn much about. Went a different route. Probably a good thing because it's really hard. Okay, so point is, understand everything that we're doing here. Because if you visualize all of this and think of all these relationships, it's going to be much clearer to you what you need to do. Okay. What's this? What's F bar delta T? It's an impulse, isn't it? We just defined impulse. It just comes right out of equations of motion. Now, the formal derivation of impulse involves integrals. It's not that much harder, but we're not going to do that right now. Okay. We'll just accept what comes from the assumption of constant acceleration. Okay. And then average values thereof. Okay, so that's impulse. And this is change in momentum because that's just M1 V1 F minus M1 V1 not, right? We see that? When I write delta P, I mean change in momentum. Okay. I could have written a capital J here. Impulse vector J. Okay. Now, delta V2 equals F12 over M2 delta T. So F12 delta T equals delta P2, right? It's just simple, but it's just telling you, if you multiply the net force on this thing by the time interval, you get the change in momentum. Just like if you do the dot product of the net force and the displacement, you get the change in kinetic energy. Okay. The difference between the work energy theorem and this one is just that this one is force times delta T, the other is force dot delta S. Okay. This all comes together with the fact that okay, delta T is the same for both masses because it comes from contact. Comes from these things compressing each other and then pushing each other apart. All right, delta T didn't come out very well there, but so change in momentum of ball two is equal and opposite to the change in momentum of ball one. They have equal and opposite changes in momentum. If the two masses don't change during a collision, like if they break apart, okay, you have this equation. But it really is just, it's this. This is just another way of writing this. And then this one can be written as I don't want to write it too many subscripts at this point. And I really don't like the equation very much because people use it without understanding any of this. So what I want to do is consider what happens if these two masses, well, 2 kilogram mass moving at velocity 4 meters per second times the I vector, in other words, 4 meters per second in whatever direction we choose for X, which is the direction that thing's moving in, okay? Collides with a 5 kilogram mass whose velocity is negative 2 meters per second times I. And after collision, negative 1 meter per second times I. I asked, what's the velocity of the second mass after collision? Can you use what's on the other board there? Stuff in orange would be helpful to figure out what do you know? Okay. Now, again, I recommend you take the information you have here and you put it into this. Don't worry about what you're trying to get. If you put the information you have into this format, you're going to figure it out without worrying about what it is you're trying to figure out. Put your information in there, then look at what you've got and look at what you're trying to find. Okay, I see people writing out things that are just going to be confusing. And then most cases, people getting confused. We write the simplest thing we can. So, and I'm just trying to give you some pointers on how to solve problems. First pointer was take what you're given, find a relationship that uses it, that you think maybe gets where you need to go. Make sure you understand why that relationship works. In other words, make sure you have a conceptual understanding, but then use it, okay? So we've already developed this. Now, this is new to you. You probably haven't mastered it yet. Some of you probably could come up here and just repeat everything I just did, maybe in your own order, in your own words, but you should get to the point where you can do that because it's pretty straightforward argument, okay? And it involves a lot of important concepts. Now, the point is, I gave you the advice to use this relationship. Make sure you understand it, but use it. So we take okay. Now, our information says that delta V1 that's not 10, that's V1 0. Make a subscript V1F minus V1 0. And delta V2 equals V2F minus V2 0. Okay, well, V1F minus V1 0, this is velocity, if this is the first mass, is 4 meters per second minus negative 1 meter per second, right? Because this mass goes from 4 meters per second to negative 1 meter per second. 2 kilogram mass has this velocity, 2 kilogram mass ends up with this velocity. So that's going to be negative 1 meter per second minus 5 meters per second times the I vector. Let's just keep the vector on there. This is all this happens in one dimension. We really don't need it. But we're gonna want I's and J's shortly when we do collisions in two dimensions. Let's go ahead and get in the habit. Okay. Now delta V2 is V2F minus V2 naught. What do we know? We know the original 5 kilograms moving at -2 meters per second. We don't know V2F. So this is going to be V2F minus V2 naught meters per second times the I vector. And we know V2 naught, so why did I even write that? It was originally at -2 meters per second. So M2 delta V2 is what? It's 5 kilograms -2 meters per second is this. And this is going to be the negative of 2 kilograms Make sense? What don't we know? We don't know V2F. So even if we don't know what we're trying to find, we say, we can find something. We only have one unknown left in this equation. Okay. Well, it turns out that's exactly what we're trying to find. Okay, that's how we could use this equation. There are other ways to use the equation. I'm not going to run through the rest of the solution. Next step, we don't have to write the I's on it because if this is equal to this as a vector, then this coefficient of I has to equal this coefficient of I. And we got to do the arithmetic. So that works. Another way to do this is we say, okay, let's find delta P1. Changing the momentum of the first object. It equals 2 kilograms times equals this, which is -12 kilogram meters per second. It's a perfectly good quantity. Got a question? Okay, I did a bonehead thing. Thinking ahead. I knew we were going from this to this, it's -5 meters per second. So I wrote that down as my initial velocity. So let's just fix that. Okay, so now that's correct. And I wrote it, I erased it and wrote it down. Did I? I don't know. Okay. So that makes this -10. kilogram meters per second, right? And that's the impulse. Okay. Delta P1 is the impulse acting on 2 kilogram mass. And if I write that down carefully, I can just leave that way. Then I can say delta P1 equals negative delta P2, et cetera. It all works out just like it does if I plug into the equation. But if I write it out this way, I'm thinking in terms of impulse and momentum rather than thinking formula. Okay. And if you're thinking impulse momentum, you're going to get better at thinking about impulse momentum. If you can plug this into the formula and solve it, you're just doing arithmetic. Okay. Now, you had to do some thinking to get the right formula, but you're going to be better if you think about it in different ways, approach it differently. Okay. So you kind of weigh that out. So what I've said is, well, we can use the equation, but we want to understand what the equation is expressing. It's expressing this. So actually, I would start with this. I wouldn't use that equation. Now, if you start with this, then you can write this equation, right? So if you use this equation, you're thinking equal and opposite changes in momentum. Why are the changes in momentum equal and opposite? Because the forces are equal and opposite, and they apply for the same time. Now that's the fundamental idea, the whole idea of impulse momentum. Okay. And everything you think about when you do the problems, probably not make the problems due until Friday. And if they're late and come in over the weekend, that's okay too, because of the test. Try to get them done as soon as you can, because next time we're going to talk about more aspects. Try to do at least some of the first few problems that I assign. And I haven't written out that assignment, but I'll do that when I post the video. Now, the first thing I'm going to do is I'm going to come up with a set of handful of problems. They aren't alternative problems for the test. They're kind of an alternative test. Okay. But this alternative test is only going to get you a C if you do it right, because it's much easier problems. So it's enough. You got your head above water if you do okay on it, even if you make a D on it. Okay. Your head is above water. And if you got time, everybody in here is demonstrated have the opportunity to do this. Make sure your work habits aren't quite there. Try to get them there. Means maybe more time. Means maybe you got to look at some easier problems before you try to do the hard ones, and I'll try to supply some of those. I think maybe you need some one-step problems to get used to the quantities, like calculate the kinetic energy of 2 kilograms moving at 5 meters per second. Okay. Kind of a problem you should be able to do in 30 seconds or less. And then some may be a little more complicated. You maybe make a connection. Okay. If the net force is this and the displacement is this, what's the work or what's the change in kinetic energy? Okay. So you have to understand that the work is equal to the change in kinetic energy. Problems on that level. Now, your book has problems on that level. I'm not assigning them. But if you need to look at them, you can. But I'll also try to provide some. Okay. Well, let's talk a little bit more about impulse momentum. I don't want to talk any more about conservation of energy until you got the problems in. Okay. Because I need to know what to talk about. I need to know what you need to know. Okay. Let's try to get those into me in the next couple of days. Doing the problems in chapter 8 help you with everything else. Gives you a broader perspective, and it will actually help you for test preparation. So a lot of people got me the first few problems in chapter 8, and they looked pretty good. So, okay. Okay, something that somebody mentioned, last person that stuck around after class mentioned is going out now. Got pendulums and springs and stuff like that. So, what do you have to know there? Well, the spring has a linear restoring force, F net equals negative kx. This implies that F delta x from position x to equilibrium is 1/2 kx squared. I didn't write it down, but the average force is going to be 1/2 of your negative kx, which is okay. And then your displacement is negative x. And if you multiply negative 1/2 kx by negative x, you get positive 1/2 kx squared. And that's the work done between position x and equilibrium. For pendulum, same thing. If it's a small displacement, that's implicit. K is mg over L. We derived that in class from a free body diagram, and you should be able to do that in the free body diagram. In other words, you should be able to do free body diagrams and for the pendulums, okay? All the various things that we've done. So here's kind of a situation for pendulum though. You got this K equals mg over L, which comes from the free body diagram, just the pendulum out here. You got weight down here, you got the tension in this direction. And the restoring force is basically the x component of the tension. Okay, again, review that if you need to. But we can also do it by just the difference in vertical position, the delta y. Okay, you do from here to here, you got a delta y. If you know the x and you know the length of the pendulum, you got a right triangle, you can solve for the delta y. Figure out the delta y. You can solve for this leg of the triangle and subtract that from the length of the pendulum. Okay. And your F dot delta y is what? Negative mg times the j vector dotted with negative delta y times j vector. And I'll make that a little clearer. Parentheses around that. This is one expression written across the picture. Negative mgj times negative delta yj. And it's going to be mg delta y. Delta y is just magnitude of the drop. Puts negative on it, it's a drop. But negative is not part of your delta y. Delta y is just magnitude of the drop, which is positive. But you know it's in the negative j direction. Okay, so you put that together. And get an alternative way to find the energy lost by the pendulum from one position, from a given position to the equilibrium position.